So after knowing all this stuff, let's talk about elastic behaviors of materials and all this stuff. What are all this? Okay, so if you remember your composite in the stress strain curve, alright, normally metal is over here linearly, and then after that there will be a certain deformations in this region, alright, and eventually it will break over here. Alright, this is for metal, but as for composite, normally it will break over at this point. So over here, composites always behave elastically, alright, or behave in a Hooke's law manner, alright, Hooke's law, or proportional manner, okay, and therefore I will have to need you to know this equation, and you have to memorize all this thing. I believe it's not given, okay, and therefore you need to memorize. These are all your strain in different directions, alright, strain x, y, z, in terms of their stresses and their Poisson ratio, alright. And I'll just go on a little bit further, is that the Poisson ratio over here, okay, comes from here, okay, is at page 56, your lecture notes part 1, okay, and as you can see, alright, your Poisson ratios 1 2 and Poisson ratio 2 1 is equals to either your so-called difference between the strains or this equation, alright, and this equation is the volume fraction of the matrix and the volume fraction of the fiber, okay. Okay, my fault, I should say that this is your Poisson ratio of your matrix, alright, and this is your Poisson ratio of your fiber, okay. So there will be a certain ratio given to you for your matrix and your fiber, and these are the volume fraction, F, the volume of your fiber, and the volume of a matrix 1 minus F. So I repeat again, these are all your Poisson ratio of a matrix and fibers in terms of F or in terms of M, okay. And then once you solve for these equations, you get your total Poisson ratio in this 1 2 direction, okay. If you don't understand anything about it, alright, and watch V2.9, alright, there is certain derivations over there, or you can watch I think somewhere at this 20.33 area, yeah, the 20th minute also, okay. I'll not go into details. Once you get the Poisson ratio, you just sub it in, alright, with the stresses and the Young modulus you also have, you eventually get your strain in different directions, okay. I may be wrong, but at least something for you to see. For how you derive this equation, I'll leave it at the end of near the end of the video, then I'll do it out, okay. So up till now, I will still continue to go on the normal slides, alright, the things that is required for you to know, and if you want to know more for the derivation part later, we will go into that, okay. So after we know that for the isotropic material, you use all this thing to find your strain, alright, then we can go on to get your shear and bulk modulus, okay, where this is your Young modulus E, alright, this is your shear modulus G, okay, in terms of your Young modulus and your Poisson ratio. So you're gonna sub it in to find your shear modulus, and I believe you need to memorize also, alright. As for your bulk modulus, you'll need to also get this, is your Young modulus again and your Poisson ratio. And the question you may ask is, why do I need the bulk modulus? Where? So the bulk modulus is a measure of the substance resistance to uniform compression, alright. It's elasticity in the ratio of stress to change in volume, alright. So it's a stress versus change in volume, alright. Not go into details of this equation because I have certain issues with it, alright, but graphically, alright, it's trying to say that all the stresses are acting on the volume to actually change it, alright, to change the volume in terms of certain compression. So when we're talking about compression, you're going to use the shear modulus, the bulk modulus. And please do not confuse this K. This is an italic word for K, alright, comparatively to this K, okay. This K, if you were to go to lecture notes, part 1, page 46, alright, you get to know that your fiber efficiency factor K is also here. So when they're talking about fiber efficiency, alright, they use thick bold K, alright, thick bold K, or these values, okay. So not every time if you see the type of K, you please note that lah, yeah. And then for the anisotropic materials, alright, these are the independent moduli for you to use. Okay, you need to read it up yourself. At least you get a feel of it. So you may wonder, what is the 21 independent elastic moduli? And I believe it's actually not 21, but rather than 12 independent elastic. Okay, why? It's because if you were to just head down to here, as you can see over here, there is 12 of it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And these are all elastic moduli. Okay, so there is in total 12 independent elastic moduli. Alright, all in all you need to know is that your isotropic material, you use this formula, G and your K, your bulk modulus and your shear modulus. Now if you talk about an anisotropic thin composite lamina, alright, your Young modulus is different, E1, E2, E3. Alright, your shear moduli, alright, is all this. Alright, and your Poisson ratio are all this. Okay, and I will believe they are all given to you. Alright, or otherwise the Poisson ratio you may need to calculate yourself, or there are other equations that you will need to rearrange in order to calculate. Alright, and you need to know that the Young modulus for E3, E2 are the same. Alright, these are the things that you need to take note of. Your Young modulus in the 3 direction, alright, this is in the 1 direction, this is in the 2 direction, this is in the 3 direction. So in the 3 direction and 2 direction they are same. In the shear modulus of a 1-3 direction, alright, 1-3 direction is actually in like this. Alright, so you have this plate. Alright, you are shearing in this form. Okay, and then 1-2 is actually shearing in this direction. Okay, and I don't need to explain for this. Also, is the Poisson ratio the same? And the reason behind why they are not, why they are the same, is because let's take a look in this so-called the laminate. Alright, this is in the 1 direction, this is in the 2 direction, and coming up is the 3 direction. And if I were to pull in the 2 direction, alright, if I were to look into this view, okay, as you can see, this is the 2 direction, this is the 3 direction. Okay, so the transverse, alright, because if you think about it, this is actually longitudinal, alright, it's the 1 direction, so they are strong in only the 1 direction because it's an anisotropic material by the word as it says. So the strongest is actually in the 1 direction, while the 2 and the 3 directions are approximately about the same. Alright, because when you pull in this 2 direction, you're actually trying to pull these bonds apart, or this interface apart. When you pull in the 3 direction, you're trying to pull these bonds apart, as you can see. So these bonds between the fibers are approximately the same in the 2 or 3 directions, and this is why the reason behind why they are the same. Alright, so at least it's easier for you to memorize. And therefore the next page coming up from here to here, alright, is exactly the thing that I'm talking. Okay, this thing over here, as you can see, if you were to look into this direction, actually the sigma, the stress 2 is pulling these fibers apart in this direction, which is the same as I've just drawn in the picture over here. Alright, it's trying to break these bonds. If I use a different color now, trying to break these bonds apart. You see, I'm trying to break them all apart. And as for this thing over here is the same thing that I've just explained. I don't need to go into there. Alright, and therefore the Young modulus for them they are approximately the same in the particular directions. Alright, and therefore now let's come to the shearing. Alright, where since I think I don't need to go through the shearing part because it's quite intuitionally there. Since the 2 and the 3 directions are the same, the shear directions is quite significantly the same also. Okay, I'll not go into the shearing part. If you are keen, you just do it yourself because it's the same analogy. Okay, it's trying to shear them apart. Never mind, I'll go through here. Alright, if I were to shear in the 1-2 direction, okay, most probably if you were to look in this direction, alright, or no need to look in this direction, you will most probably see something like this. Okay, I can't draw very well, but it's over here. Okay, so after if you shear, you're gonna shear in this direction. You're gonna actually move up. For example, okay, if you were to move up, you become like that. You see? So you're actually shearing in this direction. Sorry. Yeah, you see, so this piece is actually moving backward, this one moving upwards. Alright, this is for 1 2 direction. And if you were to look in the 3 1 direction, if you were to shear in this manner, okay, then most likely I'm actually moving up. You see, so I'm actually shearing in this direction. Alright, comparatively to just now, this one, you see, this one is in the 1 2 direction. I hope this is pretty clear. Okay, you're shearing in where? In this direction. This one is shearing upwards. This one is shearing upwards, this is shearing sidewards. Alright, in this plane. If I have to draw with a different color, alright, I'm shearing in this plane. Alright, over here I'm shearing in this plane. Okay, hopefully this is pretty clear. Alright, and therefore this is this page is trying to say. Alright, and I just want to bring up the understanding that anisotropic, alright, anisotropic and unidirectional are similar explanations, or are similar definitions, or same meaning. Alright, and there's another word called the orthographic. It's also saying the same thing, talking about anisotropic material. So these are all the 3 terms that you may come across quite all along: anisotropic, orthographic, unidirectional, or biaxial. Alright, biaxial is 2 directions, I think. I forget, but these are the different stuff that may affect the terms that are being discussed. I don't know what am I talking about, because I play quite a lot of games these days. I think I'm almost there. So I just want to give a full summarization of what we have just said in this video, because I think we might be here and there. Okay, so the key information to take away is this equation. Alright, this is to find your strain in an isotropic material. Okay, to find your strain, this is the equations, remember. Alright, then we talk about for isotropic material, alright, because you need to know your shear modulus and your bulk modulus for your matrix later. Okay, so you need to know your G and your K also, and don't mix your K with the fiber efficiency K in your slides over here. Alright, yeah, and therefore this is for isotropic. Now when we go into anisotropic, we say that these are the few stuff, Poisson ratio and things like that, and we also discussed why E3 and E2 are the same, G13, G12 are the same, and things like that. And yeah, and we graphically prove it to you. Yeah, I think this is the kind of understanding of for you to take note of. Alright, and you can go now. Alright, otherwise I will start to derive these equations, alright, which is I don't think is in your syllabus, but yeah, in case in the future you may need it. Okay, so you can just leave the video now, and if you want to continue, you can continue here. Alright, so I may not necessarily derive that because this is my first time trying. Alright, so the strain itself, you remember, is the change of length over its original length. So original length is here, alright, and this is the change in length, right? So change in length over its original length is your strain. This is the definitions. Alright, as for your stress, it's just stress is equals to Young modulus times your strain. Alright, and you know that your stress is equals to force over area. Alright, so we can simply write as stress is equals to force over area is also equals to this one. Alright, next, we know that the strain is equals to change in length divided by L. So I can simply sub my strain, alright, as this term. Okay, so what I would have is like this. Okay, so if I were to clean things up a little bit, yeah. Okay, and then next, I know that my stress is equals to Young modulus times strain, correct? So all I can do is simply to rearrange in terms of Young modulus. Okay, so I have stress over strain is equals to Young modulus, and I sub this into this thing. Okay, so what I would have is form. Okay, and then now I'm still gonna bring this up again. Alright, so in other words, this Young modulus I change to this one. Okay, so I just want to show you in a neater way, so that's why I cover up here again. Okay, next, alright, I'll just simply bring this A upwards, I'll bring this change in length downwards. Okay, and therefore if I were to do that, I'll have F equals to stress times area divided by strain times length. And this equation is what you have seen over here. Okay. Nonetheless, I believe you have the ability to also write in terms of this form, but I don't see the link to how we derive the equation over here. Alright. So therefore what I thought is that what we have just said earlier is also something that is not related to us. Okay, but at least you get to know how the things are being derived. But next, I'll just simply take on the understanding of stress is equals to Young modulus times strain. Alright, so this is the second attempt that I'm trying now. Okay, so next I'll just sub in my let me see. Okay, now I'll sub in my strain as equals to I'll just move my Young modulus down. Okay, in other words, I'll have this strain. Okay, so taking that, I will assume that if my strain, alright, is equals to, let me see. So I would believe we may have certain assumption, alright, that the strain in X and Y, alright, as to be the same. Okay, so if changes in the X direction is the same, for example, if you think about it, let's look in a 2D form. Okay, let's look in this plane. If you were to take a look in this plane, okay, so this is the plane, this is our X, this is our Z. So if I were to pull X in this direction, the strain in the X is this. Alright, this is the strain in the X direction, and then the Z direction will change. Alright, there will be a Z direction that is, so in other words, you'll see that your material is somewhat like that. Alright, so this is the strain X, and then over here this is the strain Z, correct, in the Z direction. Likewise, if you were to look at the this plane, alright, which is the ZY direction, you also get to see the same phenomenon that has occurred. Alright, where the Z, alright, the strain in the Z direction would change. Alright, so we assume that the strain X and strain Y has the same amount of strain, so that the strain Z, then we will know that the strain Z is a certain amount of strain. Okay, I know my explanation sucks. In simple terms is that I will assume that the X and Y stresses are about the same. Alright, because I just want to ensure that the strain in the X and strain in the Y directions are the same, such that we will know the exact strain in the Z direction. Okay, I don't know why must we do that, but I just take this assumption so that we can get to see a certain meaning in there. Okay, so we know that there will be a strain Y over strain X, for example. Okay, so over here, if you remember, okay, a strain in one direction divided by strain in two direction is equals to a Poisson ratio in the 2-1 direction, I think. Yeah. Alright, this definition comes from this slide. Alright, lecture note page 1, lecture note part 1, page 56. Okay, where this is your equation for your Poisson ratio, and this is the so-called method that I've been using. Okay, so therefore in this case, we can also take that strain in the Y direction divided by strain in the Z direction is equals to strain in the X direction divided by strain in the Z direction, because we assume that the Y and the X strain are the same. Alright, and setting it as equals to minus V, the Poisson ratio. Alright, so knowing that my Y and the X are in the same direction, in the same strain, having the same amount of strain, then I would say that I can simply take this strain in the Z direction to sub it into here. So this is what we have. Alright, let's do it individually. Okay, so if I were to bring this upwards, what do we have? We will have, alright, strain Y is equals to minus Poisson ratio strain Z. Minus Poisson ratio is because when you pull in this direction, okay, this thing is going in the negative direction. It's minimizing. Alright, it's being compressed. Alright, this is why there's a minus sign. So this is for strain Y and strain Z. Same thing if you were to have strain X and strain Z, for example. Alright, then I'll have a similar equation. Instead of y, I'll have strain x. Okay, and this explains why, alright, your strain x is equals to your strain y is equals to minus strain z, Poisson ratio times strain z, which is exactly this equation over here. Okay, and next I'll change this strain z. Alright, since we know that stress is equals to Young modulus times strain. Alright, so I'll just write in terms of a certain strain. So this strain can be written as stress in the z direction is equals to E. Okay, next I will bring this strain, alright, since we know this Hooke's law, okay, so I also simply rewrite them as stress x over E is equals to stress y over E. Okay, and after a long while I still can't figure out, and therefore yeah. But anyway, in the future if you really need it, then you can just go and search yourself lah. But this is where I will stop here. But just want to go through the equations so that it's easier for you to understand. Is that your strain in the x direction, alright, is equals to your, if you were to multiply it in, if you think about it, the Hooke's law is stress is equals to E times strain. Alright, so if I were to bring this E downwards, I'll have stress over the Young modulus, which is this one. Correct? 1 over E times this one. And then 1 over E times this one is the stress, is the strain, alright, in other directions. So in other words, alright, this big portion over here is the strain in the x direction. Only purely for the x direction. And then over here, multiply with 1 over E. If you were to multiply everything inside into here, alright, this over here is to minus away whatever thing that is coming from the y and the z direction. Because if you were to have a strain on this cube, alright, then one direction over here, or the other two direction will definitely go somewhere else. Alright, and therefore this is intuitionally the case. Hopefully you get what I mean. If I were to multiply this thing in, okay, I will have this one. Alright, so 1 over E times this one, 1 over E times all of here. Correct? And then next, alright, if you think about it, your stress strain curve is, your Hooke's law is this one. Alright, so if I were to rearrange, I'll have this thing. Okay, so your strain can be in terms of stress Z divided by Young modulus itself, which is this equation. Alright, but this is only for the case of a 1D. Alright, for a 3D, alright, because if you have a 3D cube over here, if you were to have in the Z direction, if I were to pull in this direction, alright, this direction will kind of compress, alright, this direction will also be compressed. So what you'll see at the end of the day, alright, something like this. Alright, so this is also being, so in this direction is compressed, in this direction is also compressed. So you have to take note of all the total stress coming in, or all the total strain also. Hopefully this is pretty clear so far. Alright, this is the meaning of that lah. But if you want me to derive, I don't know how to like really theoretically derive. But yeah lor, this is the thing lah. Alright, and in the next part, then we'll start to talk about the main key things all over here. Okay, see you there.